All right, so at this point, everything we have learned are all the transformations that happens on the vertical axis, right there, or all the transformations in respect to the vertical axis. Meaning we've studied thoroughly in details about the vertical shifts up and down, or the vertical scaling, okay, causing it to either vertically stretch, vertically compressed, or flipped through the x-axis. So in other words, it's a vertical flip right there. Okay, so those are all the elementary transformations that happened in respect to the vertical axis. So now we are ready to make our way out to the to study about those transformations, those elementary transformations that are in respect to the horizontal axis. Right there. Okay, so now let's look into among the horizontal the transformation. Let's look at the horizontal shifts. Okay, so now that's what we're heading into next. So horizontal shifts. All right. So we're gonna again go into quite in-depth details again, and we're gonna find out what causes a graph or a function to be horizontally shift to the right and shift to the left. That's what horizontal shift means. Okay, so now let's have a look at the graph here, so that I can quickly explain what it means by the horizontal shift here. So let's say we have a graph, whatever the graph of whatever function this graph represents. But so a horizontal shift means, and so now with a graph in blue ink right here, and the blue is the transformed version of the red, but right now the blue is staying right at the same seat with the red function. So we want to find out what causes this blue to be shifted to the right and shifted to the left, or what causes it to stay in the same spot compared to the original parent function. And again, my point here is that, and I keep mentioning, none of the transformations here will cause the graph to change to a different shape. So whatever the shape of the parent function that came out with, any transformation will just stay with the same shape. Some scaling may happen, as you have already seen, but it won't change the shape. For example, here it's a cup. Okay, it's not going to turn into a loop. It's not going to turn into a straight line. All right, so that's the idea right here. So right now, again, specifically, we want to find out what happens, what causes the graph of a function to be shifted to the right or to be shifted to the left. And that's what horizontal shifts mean. Okay, so now, in that way, again, let me introduce a parent function. And then from that parent function, I'm going to introduce a descendant function. Okay, and so all of these terms you have learned throughout our time that we spent studying about the vertical transformation. So now, hopefully at this point of the lecture here, anyone has viewing the lecture has been quite familiar with those terms. The parent function, the descendant function. I also have my own personal term, the guiding points and all that. Okay, so let's bring all of those in here. All right, so now as far as the parent function, let me choose to work with the following function. So let's work with f of x equals x squared. Again, okay, we may or we may have not worked with this problem, but it's just one of the functions. Whether you recognize it, whether this function appears to be common to you, that's not important at this point yet, okay? But it's a function, and now I call it's a parent function. So now let me come up with before I say it too clearly out, before I say it out too clearly, let me define a different function for you to understand it's a different function. But this g of x here is defined, how about x minus 2? Let me write that 2 in red ink purposely, okay? X minus 2. Okay, x minus 2 square. All right, x minus 2 square. And I'm not saying anything about descendants function or anything like that. And all I'm saying is, all I'm seeing right now at this moment, this function here is a function that is different from f of x. I name it g of x. Okay, so g of x equals x minus 2 all squared. Okay, and so now let's have a closer look for here. So in the way how I see this, at least this is how I at least this is what caught my attention in this function g of x right here. What caught my attention is this square. Okay, now so comparing this g of x function that has the square with the one I call the parent function right here, because sometimes you have a lost child and it's hard to recognize if the child belongs to that parent. Think of that idea right here. So what's the common trait so that you can recognize a child belongs to a parent? Here the common trait is this square. It has a square. So think about this. What I see here is that it has a square, so couldn't this g of x function, I'm saying couldn't this g of x, I'm trying to point out that thought process right there. Couldn't this g of x come from some square function? Some square function. And then instead of squaring just a simple x, instead of squaring the simple x, this square here is the square of an x minus 2. Okay? That's what I'm trying to break down to see how this g of x happens right there. So like I said again, I was pointing out that since I noticed there's that square being common with this parent function. So I'm starting to think, possibly can this g of x here come from, okay, can that g of x possibly, or could that g of x possibly come from the simple squaring function? Okay? And then squaring that, but now instead of squaring the usual simple x, okay, because if this is just x squared, then it's the parent function, needless to mention, it's the parent function itself. But now instead of squaring the simple x, it's now squaring an expression. It's squaring x minus 2. All right, so now this is the way how I see it. So after all of that work pointing out right here, this is how I'm seeing. So having that square right here really is the function f. The squaring rule right here, I recognize it. So it has that thing from its parent. It has that trait from its parent. The square is the rule from its parent. But now, furthermore, I recognize that, hey, so in the end, it looks like g of x is simply f that takes x minus 2. G of x is f of x that takes x minus 2. Okay? And so now at this point, so at this point, maybe I have said this earlier in the beginning of the video lessons, or if in case I haven't, now I mention it. This video lesson here, and particularly at this part of the lesson, it is highly recommended that you watch or you learn from this lesson after you have learned about composition of a function. Okay, a function, the composition of two functions, or at least you have learned about those kind of advanced evaluating functions where you take an expression and evaluate that into a function right here, because this is the one. F of x is simply just that simple rule. You square the inputs. But here, instead of the usual input x, the inputs here is an expression x minus 2, throwing in the role of the input of our function f. All right, so now I see that g of x is now clearly the descendants function because it comes out from the parent function. It came out from the parent function, but we created g of x by simply putting the expression x minus 2 inside of f as the input for f. Okay, so now clearly I can now call that this is the descendants function. Okay, so this time my approach is slightly different with how I've been doing that in the earlier transformations. In the earlier transformation, I just came straight into kind of, hey, here you go, that's the descendants. Here I'm treating that as just, and my intention here is to show people also a thought process so that a lot of times later on you can pick up on that tricks of mine to be able to recognize fluently which function is possibly a descendant function from a parent function, because that kind of work can become challenged sometimes. So here we just start out with a function that we may not know for sure whether it would be a descendant function from a parent function or not. But now after some consideration, now we're more firm that it should be a descendant function. Okay, and then we can confirm. So f of x, think of this f of x minus 2 right here. If we would write it down, okay, in math, then the rule for f is the squaring rule. Okay, and then x minus 2 is the inputs. And so that is clearly g of x. So this third step right here is just simply the confirmation. the work that I'm confirming this relationship between G and F right there. All right, so now in this way, we're looking at G of X here being the function F of X minus 2. But I put this 2 in red ink right here, and for now it's a minus. Okay, it's a minus, and then it's a 2. And then I put that 2 in a red ink, and then so if we pay attention to that red ink right here and ignoring the sign right here, then that 2 here itself, I want you to see that it's a positive 2. And then we'll subtract the expression here, say x minus a positive value, x minus 2. Okay, so that's just now I pointed out how G is related with f of x, so clearly or apparently G is a descendant function from this parent. Let's now have a look at the graph. Okay. All right, so in my graphing screen right here, in full screen view right here, this is actually indeed the graph of that common function of that parent function f of x equals x squared. It's written in red ink, being consistent with what I've been doing right here. Anytime we're looking at a parent function as a convention throughout my entire lecture here, then we're writing that in red ink. Okay, so the graph is also in red. So this is that famous parabolic shape right there, or it's just that famous parabola for this simple quadratic. That's how I call that. And then at this point you can recognize, or you may recognize, or you may not recognize. That's not too important yet, but this is one among the toolkit functions that I'm demonstrating. Okay, and so now I've also brought in the guiding point. So now let me show the guiding points. I explained about the guiding points throughout the earlier part of the lesson here. So these are the guiding points that can be found on the graph for f of x. Okay, so these are the guiding points right here, and they have the coordinate values are all being displayed here. Okay, so now this is going to be the graph for g of x right here. All right, so this is the graph for g of x. So now as the graph for g of x just popped out, and I didn't show the step-by-step how I get there. I'm just telling you that. And you can do the same thing right now at your learning, at your experimenting step right here. Think about, you can use your favorite technology device. I've showed you the techniques that to work around with the TI calculator. I also show in some other earlier video lessons how you can work with decimals. And there are many other technology resources out there where you can use for your quick graphing purpose. Graph this parent function, put it in red color if it's possible for in your technology. Then graph this function. These are all easy syntax on the graphing device right there. Graph this parent function and graph this descendant function. Okay, put them together, and possibly, if you could, put these in the appropriate colors right there, so that you can see where the parent is and where the descendant one is. Okay, and that's what we are seeing right now. Okay, so that's the idea. It doesn't have to be decimals like what I'm using here. It can be whatever favorite graphing technology that you have. Okay, so now again, so once you see the graphs of both, let's make some good observation. So it looks like the graph for it, and so here I'm using blue ink, okay, blue color to represent my g of x, and my f of x is here. So it looks like g of x has the exact same shape. G of x has the exact same shape. It's right there, exact same shape. Exact same scaling as well. How wide, how vertically stretched, or how wide that is exactly the same on the scale. It's like really one-to-one scale. The only difference, g of x, the blue one, is being shifted to the right-hand side. Well, how do I know that? Now let me bring it in closer view right here. You see, for a parabola, it's always easy to look right at this vertex right here. See, the vertex of the original parent function stays right at the origin 0, 0. But now let's look at the vertex on the vertex on the blue version. And now it's probably a good time now to put in the actual guiding points on the blue version so that it's easier to see. Okay, see, so now the vertex, the corresponding vertex on the blue graph on the descendants function is right here. So it's still sitting right on the x-axis, but it's being shifted to x grids to the right-hand side. How do I know that? Because x equals 2 is indicated right here. All right, and so now we start seeing that shifted, the whole graph there, shifted as is to the right-hand side by how far? 2 square grids, and you're still seeing that right there. All right, so now let's write down that observation, whatever we noticed right there. So now again, what I notice here, I want to see this form. I want to see this form as a x minus, okay, x subtract, but then the 2 here is some value here right now being positive. Okay, x subtract, and then right now that 2, that's why I wrote it in red right there. I want you to focus on that 2. So aside from that subtraction operation, then I want you to see this value as a value after a subtraction operation. So now in the way how it is right now, that value in red is minus 2. Okay, and so now, so the observation we saw according to the graph right now. Okay, then the graph is shifted. Okay, shifted, but here's the observation I've seen right here, and you are seeing that with me too because it's still on the screen right there. It's shifted to the right. The graph is shifted to the right by 2 units. And when I'm saying units, you have seen this in the earlier explanation, but so now let me clarify again. 2 units here means, see, look right at the picture, it's being shifted away by 2 square grids right there. Whatever the grids that happens with the graphing space. So the graph here is shifted to the right. Okay, shifted to the right, or is moved to the right 2 units. So let's check for some consistency to start clicking right here. So 2 units, okay, does that make is there some connection between the shifted 2 units with that 2? Oh yes, that's what it is. See, so this 2 right here explains for 2 units being shifted away. Okay, and then because the 2 here, see, like I said again, I want you to focus on the fact that the operation here is a subtraction operation. So x subtract a positive value. Okay, so positive value cause going to the right hand side. So let's put that observation here for now. Let's make another one. Allow me to hide away the graph for now. Okay, so at this time right here, now I'm going to erase this. So we're starting to see where we're going a little bit. You're starting to see where I'm going a little bit. That the general thing here is that it's going to be g of x be the function that takes some x minus a value. Okay, some x minus a value. And that's why I have this. This is g here is f from the parent's function, but takes the input as x minus 2. All right, so let's confirm our understanding. So I'm going to call that a different g of x, just to confirm our understanding. A different now, and I'm clearly I'm firm that this is a descendant function I'm about to write down right here. So how about another g of x? But now I'm going to call that f of x minus, and like I said, I always want that operation here to be minus the operation in the input expression right there. X minus, and now let me put how about okay, this comes out from my random creativity choice right there. I mean random choice of creativity. Let's create something like that. So algebraically, this is written as g of x, or as a final expression. So f of x minus 5. So now I'm going to take x minus 5. You have learned that technique already. So x minus 5 being the input of the rule that squares every input. So this rule, the rule that squares every input, comes from the parent function. But now the inputs here is being an expression x subtract 5. Okay, so now I notice again, 5 is positive, see, and because like I said, aside from that operation, and I want that operation we always want to see that operation as a subtraction operation. So now after that subtraction operation, the number here I'm writing in red is a positive value. Let's note that down. So now at this time, before seeing the graph, I am expecting, think about what we have seen earlier. So now I'm expecting, okay? So this is the expectation right here, or what's expected. I'm expected that the graph of f, of course, okay? So g is the graph of f of x, but then being transformed, okay? So it's basically expected the graph of f of x being shifted, okay, is shifted to the, this is a positive value, so it's shifted to the right, okay, by how far, okay, shift, but how far do we shift that? So shift means we move. Where do we move? Where do we move? We move to the right hand side. By how far? By 5 units. Well, but everything I'm making here, everything I'm doing here is only a prediction, an expectation, whatever I expected. Okay, and so let's see what we expected here appears to be correct or not. Okay, let's see if that whatever we expected here is correct or not. All right, so in that way, here's back on our graph. This is the graph of the parents function. Okay, and so now this is the graph of g of x, which equals f of x minus 5. Or in other words, this one in blue here, this graph in blue here is the graph of g of x equals x minus 5 in parentheses square. That is the one. Okay, and I can also show the guiding points. Okay, so now these are our blue guiding points, the guiding points that belong to the transform graph. And then right here, I can put in the labels right there for that. All right, so that's so now all of a sudden we feel like it's confirmed. Our observation that we made earlier confirms that anytime we put an x minus a positive value inside of a parent function right here, okay, then we're gonna shift the graph of the parent function. We're gonna shift, so the graph of the descendant function here is created by shifting the graph of the parent function, okay, to the right. So subtract a positive value here, shift the graph to the right by that many units far. Okay. But now, so we're close. We're over 75% close to our complete understanding of all the horizontal shifts here. Let's put in things a little more. Let's look at another scenario over here. Okay. So now I'm going to put this away. All right. So now let me just simply write down the function as following. How about g of x? This time I'm going to, and I'm just saying it's a descendant function. But let's look at things this way. How about I'm going to put g of x here as f of x plus 5. It's not x minus 5, but if f of x plus 5. F of x plus 5. This is a very common way of seeing it. This is a very common way of seeing it. Okay? But here's the thing. This is my this is how I'm approaching a problem like this. So when I see f of x plus 5, then I ask you to see this g of x as f of. So at this point, learning in this lesson, you are fluent enough with the operation that plus sign means x minus. Okay, it's x minus. So there we go. I'm starting to bring it back to that convention I've been yelling out loud earlier. I want x minus because here it's a plus. It's not the operation that I've been asking everybody to pay attention to. So now plus 5 is the same as minus negative 5. Yes, it looks a little problematic when you're seeing a form like this. But now I write this down for a purpose. Now we are landing into that form x minus, x subtract the operation here. We purposely use that as a subtraction operation. So x subtract But now the value here, so x plus 5, yes, a lot of algebra textbooks, a lot of college algebra textbooks or pre-calculus textbooks write the transformation this way. But I want you, my students, whoever learn with me, to see this, even though it's a plus right here written so clearly. You see that as a minus. You see that operation here as a minus, but we're subtracting a negative value. So in this case right here, minus 5 is the value, right? I'm extracting out that information in this. So the only different in the situation now is that we're looking at subtracting a negative value. Subtracting a negative value. Okay, and so now here's how I'm seeing it. Let's now put the graphs in, okay? And I already said this is clearly a descendant function, but we want to see a little more clearly how this descendant function is changed, is different from its parent. Okay, and I've walked through 3 little examples so far. None of the descendant is exactly the same as the other descendants. Just like, one parent can have many siblings, but, none of the siblings is exactly like any other sibling. Okay, there has to be some little difference in the trait. Okay, so now on my graphing screen, this is the graph for the original parent function, that nice parabola. Okay, and so now let me put in that the graph for g of x equals x plus 5 all squared. And I should have mentioned, so in this way right here, I'm seeing that algebraically this is the same as, yes, I should have mentioned that, x plus 5 all squared. That's the function for that. G of x equals x plus 5 all squared. Or right down here, g of x is the same as x minus negative 5, okay, all squared. So this is the actual rule that if you use a technology, type this in to your technology or type that into your technology, and it will pop out a blue graph like that. Okay, so that you can have something to compare with the parent function. All right, but now let's really look at the graph. So now on the graphing screen right here, this is the graph for g of x equals x plus 5 in parentheses square, or another way of saying x minus negative 5. Okay, one way you're saying x plus 5 all squared or x minus negative 5 all squared. This is the same thing, but I prefer my students, whoever learns with me, to see this as x minus negative 5. Okay, x minus negative 5 all squared. All right, and now I can also put in the guiding points on this blue graph. And the guiding points up here, all of the guiding points are now displayed here. Okay, so now what is the observation? The graph in blue here stays exactly the same scale, exactly the same shape with its parent. Okay, but the only difference now, it's being shifted to the left-hand side. The left-hand side. That explains for the left-hand side. That explains for moving it to the left-hand side. Okay, and now by how far? So it looks like by counting the grids right here, we notice that this graph is being shifted. Okay, so left or right, it's indicated by the sign of the value, but then how far? 1, 2, 3, 4, and 5 square grids right here. Okay, so in that way, now let's write down the observation. So now I'm seeing that the observation here I'm seeing is that the graph is shifted. Okay, the graph is shifted, but this time to the left. Okay, to the left, and that is explained by this value being negative. See, so x subtracting, you putting it inside your parent. So at this point, we start forming that generality right here. If we're putting it inside the parent's function here, we're putting into the input of the parent function here an expression that x minus x subtract a value. That's going to cause some shifting left or right. Okay, so shifting left whenever we subtract a negative value, shifting right whenever we subtract a positive value. Okay, So it has to be x minus, in the way how I want my student to really catch and have that solid, crystal clear understanding. X minus, the input expression is x minus a value. That causes the shifting. And then shifting right is when it's minus a positive value, and shifting left is when it's minus a negative value, like this. And that's why now the graph is shifted to the left. Okay? But by how far? By 5 units. Okay? By 5 units. I have a reason to show so much space here, because I want you to understand a little further. So yes, we say 5 units because we have the grids here when we count. Okay? But mathematically speaking, 5 units here is the same, or is the same. Another way of saying it, because here's the thing, 5 here is just counting the units, but not always we have the graph available immediately, and not always our graphing technology shows the units clearly. Okay, so 5 units here, another interpretation of that is 5 units here is really absolute value of that -5. So take the absolute value of that subtracted value here, regardless of it being positive or negative, but take the absolute value. It will clearly indicate how far absolutely the graph's being shifted, because the sign here is responsible for going left or going right, but the absolute value is responsible for how far absolutely will the graph be shifted. Okay, and so now at this point we are ready for getting into a general rule, okay, of this, getting into a general rule of this. All right, so now I'm going to move to the other page of my board. All right, so here we go. So I'm going to start out with, and this is the rule, this is what explains, right? This is the rule that explains the horizontal shift. Again, I have to make it clear. So let f of x, okay, be a function. And of course, we can also call that a parent function. So any function can be a parent function. Let f of x be a parent function. And so whatever the function defined as g of x, that equals g of x equals the parent function that takes input x minus. That's why I've been spending so much time yelling out loud. I want you to see that this is x subtract. The operation here is subtract. Okay, so x minus a value a. All right. So any function g of x defined as the function f, that parent function. Okay, but take inputs x minus or x subtract a value a. And at this point, a could be positive, a could be negative, because in a general rule like this, we've considered a lot of cases earlier, but now generally speaking, a here is just a value. It could be positive, it could be negative, it could even be 0. Okay, but generally, anytime we're defining a function g that's from the parent's function, taking the input as x subtract a value. Okay, then this function here, okay, g of x as defined as that, has the graph. Okay, has the graph of f of x. Just like how I wrote down the that general rule for vertical shift. So here, this descendants function will have the graph will carry the shape of that graph of f of x. Okay, but then shift it. Okay, shift it. I mean, of course, we know it's horizontally. Let me skip that term horizontally. Let me break that into 2 cases. So so this g of x has the graph, which is the graph of f of x, but shift it. So on one case, shift it to the right. Okay, so that's indicating it's a horizontal shift. So I don't need to say shift it horizontally. Okay, so this g of x will have the graph of f of x, but the shifted version, shifted to the right. But by how far? By absolute value of a. Okay, by absolute value of a units. If if A is a positive value. If A is a positive value. All right, so underline that, or put that in a red box or something like that to highlight that. Okay, so that's one statement. So anytime that we're doing x minus 5, see 5, it's x subtract. That causes the shifting, the horizontal shifting. But then the positive value, that causes shifting to the right-hand side. And then by how far? Absolute value of this. Okay, so if it's just x minus 5 here, for example, or x minus 2, like how I brought up earlier, then that's just by how far? By 2 units far, because it's absolute value of positive 2, which is 2, needless to say. Okay, so in that way, to continue with this generality right here, okay, g of x defined in this way. So this is sort of like a real generality, or the real point of generality right here. So that g of x defined this way, related to the parent function in this way, we'll have the graph of f of x, but shift it to the left. Okay, by shift it to the left by, again, so the rule that we can see now is how far we shift. It's always absolute value of the number here. Okay, so absolute value of A, units. So that many units, absolutely that many units, absolutely that many units. Okay, if A is a negative value, okay, and put that in a box again. All right, so that formulates our general explanation. What causes, so this is any of these cases right here, is what causes the graph of any, or what causes any descendant's graph being the shifted version of from the parent's graph. How's that? All right, and so now let's get back to the other board and start applying our understanding into doing some example. Okay. But now, even though I said so, I wrote down the generality. But again, just like the earlier transformations that you have learned, when it comes to a practical situation, when you really are doing a problem, it's not always easy to think about holding a graph, shifting it to the right, or holding a graph, shifting it to the left. It's easy for somebody, because somebody has stronger visual sense than somebody else. Okay, that's the experience I've seen throughout my years teaching. And so allow me to show another advice, one advice that generalizes everything. Okay, one advice that generalizes all of this concept, so that it's for the people who are strong at visualizing and feeling easy, that they can just simply take a graph, move it as is to a few units to the right, or move a graph as is to the left. For some people who are doing that, who can do that easily, that this advice can still be useful, and especially for the people who are not so strong with your visualization skill. This advice I'm about to show is going to be a tremendous help right there. It will guarantee that you will always have your graph shifted correctly when you're on your own and doing everything on paper and with pencil. Okay, so just like that, I picked up this advice from one of my favorite professors back then, when it was my time learning about this. Okay, so now as far as the advice, let me now point out that advice right here, and then we're gonna, all right, and so before we get into any formal example, so that advice for horizontal shift here that I would like to share, that I would like to show. Okay, and now it comes to an advice. So, you know, if this advice of mine doesn't click well for you, you can also learn from other professors here and there. Okay, and they have other advices that will click for you. That's why outside from watching my video, you're more than welcome to learn the lessons from any other professors as well, and also read the textbooks that comes with your course. Okay, so the advice here is that we add A. Okay, A is that. Recall that it's f of x minus a. A could be positive, A could be negative, but we, in the world of algebra, everything is an add. Okay, so this expression in particular is one in the rare times I want to show it's x minus. So I use subtraction here. Okay, but in a lot of calculation algebraically, it's all about adding. Okay, so even though a is a negative, then we're still going to add negative to a value. So the advice I'm about to share here, in order to horizontal shift correctly, okay, in order to shift correctly on the x-axis, just simply add a, okay, to every x value this time. Add a to every x value. That's the advice again. That's the advice. All right, so now at this point, upon showing the generality and having the advice here, let's now apply our understanding into some actual work right here. Okay, and we're doing some work, some direct example where it has all of that skills about how we can horizontally shift a graph. Okay, so now let me clear out this board right here. All right, so the advice I have, let me write down this advice and put it somewhere in the top corner right here. So add a, okay, to every x value. All right, so now after saving a little space of the board here for keeping that, let's now look at our next example in this current lecture, example 5. Okay, let's look at example 5. So again, I'm doing the function, the problem as following. Let f of x, okay, be represented by the given graph. All right, so let me pause this statement right there before we advance further into completing that instruction of the problem. Let f of x be represented by the given graph. That means we already have the function f of x defined. It's just sadly we don't know a clear rule for that, for f of x right there. Okay, so we only know the graph being already represented by a graph. So let me now bring up the graph. All right, so this is the graph of our function, our tentative function that we're working with. Okay, so whatever function that is, it has this shape right here. It has this given graph. All right, and so now I'm going to put it in a little corner of our screen right there. So let f of x be represented by the given graph. That is the graph you're seeing. Okay, so now I'm going to go ahead and continue the writing instruction of this, the written instruction of this example. So I want to sketch. So let's sketch the graph, okay, of the following function. All right, so sketch the graph of the following function. All right, so here we go. So now I'm going to show problem A right here. So that means now I'm treating f of x here with that graph right there as the parent function. So now let's graph g of x. Okay, let's graph g of x to be, how about f, whatever function that is which has this graph. Okay, f of x minus, see, x minus, so this is giving us an expectation already that the graph that we eventually graph in blue will be shifted, okay, will be shifted horizontally, but I'm not knowing to the left or to the right yet. 3/2. Okay, f of x minus 3/2. All right, so this is the one that we're about to graph right here. This is the one that we're about to graph. So now before we advance, so this is the thought process. This is how we apply our understanding into and nail that down into formal steps right here. So what I notice now is that it's just a note that I noticed. So 3/2. See, so we always, rule of thumb, we strictly have to put this operation in subtraction. So we have to put it into x minus or x subtract, because that will show the horizontal shifting nature. That will confirm for us that there will be horizontal shift coming ahead. Okay, put that in x subtract. And so now once we notice there's an x subtract, whatever the value that comes after the x subtract, that's the value that we're going to focus to. So now this is what I know about that. So this is A right here. That's A. So further we know that, so A now is a 3/2. So it's positive. Okay, it's a 3/2, it's positive. So now there are a couple of expectations here. So A being positive, that means I'm going to shift, right? This graph is shifted. This is the expectation. It's shifted, okay? So as an expectation. So what I expect from this graph, okay, what can be expected from this graph is that, okay, graph is shifted. See, that's because we have x minus or x subtract. So the graph is shifted, but shifted to where? Shifted to the right hand side. See, because positive value. So shifted to the right. All right, shifted to the right. By how far? By, now, ridiculously, it's 3/2 is already a positive value, but absolute value of 3/2, which is 3/2. By absolute value of 3/2, or just simply 3/2 units. All right, 3/2 units in fraction, but in actual units, it's about what? 1.5. Okay, 1.5 square, 1.5 square over to the right. That's the expectation. All right, but so what? I mean, this way of expectation, yes, like I said, this is clearly what will happen. But doing this is not easy. I mean, especially when you try to take the whole graph and bring it to the right-hand side. It's easy for somebody. It's not, but it's not easy for a larger majority, for a bigger group of people, of students whoever are doing this kind of problem. Okay, so now in that way, stick with this advice I've had right here. We're just simply going to add A to every x value. We add A to every x value. So what does that mean? That means now I'm going to start utilizing those guiding points that I've been introducing again. Okay, any graph, you can just, once looking at the graph, once looked at the graph right there, okay, you can easily recognize a few guiding points, because those guiding points help easily defining the shape of the graph. Okay, and so now I'm gonna recognize those guiding points, because add A to every x values, technically or literally speaking, you have to add A, you have to add 3/2 to every x value on this graph. But we don't have to do that for all x values. Okay, just focus right on the x values of the guiding points. The guiding points. Okay, so now in that way, let me put the graph in full screen view here. Okay, so now I recognize that there's this special point. It could be a good candidate for being a guiding point. There's this point right here. It's right on the grid. It qualifies to be another good guiding point. And you can see that the graph does a straight line before that, and then doing a waving nature between -2 and 2. So these are all good qualifying guiding points right here. And qualifying, I mean, they stay right on the qualifications. They meet all the qualifications to be considered, to deserve our attention, to call them the guiding points. Okay, so now let's put those in. Okay, all right, and put the labels in. And so now clearly they have all of those guiding points. All right, so now I'm gonna, and we know that the graph is gonna be, the blue graph eventually I'm gonna put in is gonna be to the right hand side right here. So in that way, allow me to allow me to kind of shift this, bring this viewing window to the left a little bit, so that later on the graph, the next graph is going to appear to this side right there. All right, so now I'm going to move to my other board. So, well, I've left this here long enough. Let me now clear that out. So yes, even though we had a solid understanding, but it's not too useful sometimes. Okay, so stay with that advice. So what with that advice, I recognize the following table of values here. So let me now list, just like how we have been doing the earlier problems. So f of x, the original parent function, has the following guiding points here. One of them stayed at minus 2, 0. Minus 2, 0. Okay, and we had another one that stays right at minus 1, minus 1. Okay, we had another one right at 0, 0. Okay, we had another one that stays right at we had another one that stays right at 1, 1. Okay, and we had another one, and it's still on the graph right there. That's, you can always look along with me. And we have another one at 2, 0. All right, so those are enough like that. And again, so I've had this advice before. I mean, not this specific one, but this is now just a personal advice here. But try to nail down the actual shape of the graph. That's just some experience that no one can directly hand it down to you, even though I'm trying to give that advice here, but there's no way for me to hand that down for you. You just have to practice that on your own. Imagine that you can close your eyes, okay, and the shape of that graph is still in your mind, it's still in your imagination. It's going like in the way I remember about the shape. It's going up as a straight line, okay, zigzag down, okay, going up, zigzag down, zigzag up, and straight up, okay. That's the way how it is. And so now, and that's the shape that exists between these guiding points. All right, so now I am going to draw the version of f of x minus, but now 3/2, and this is about the descendants function. Okay, so that's why I'm writing that in blue ink, and the graph will appear in blue ink. Okay, in blue color. So we add, so when seeing this, it's, yes, at this point somebody might have realized already that it looks a little counterintuitive that the expression shows x subtracts 3/2, but we add, in my advice, we add a to every x value. So this is the a. So this subtraction here is simply because I asked you to make it simple. I asked you to always write it in x subtract. So x subtract here is sort of like just an indication that we will have horizontal shift. Okay, but then how far we shift and where we shift depends on this a right here. So if that a is positive, we shift to the right. If that a is negative, we shift to the left. Okay, so x minus x subtract here is just a way to indicate we have horizontal shifting. Okay, so now I'm going to add this a. And now regardless of a being positive or negative, we always going to add. So being a positive 3/2, I'm going to add positive 3/2 to negative 2. Okay, so 3/2 plus negative 2. And we add a to every x value. So tell you what, these values on the y, I mean these y values right here won't change. Okay, they stay the same. So the first pair of values, 0 for y, it stays the same because it's y value, it won't get changed. The x value here will be added with positive 3/2. Okay, so 3/2, I mean negative 2 plus a 3/2. All right, so it's giving me a negative 1/2 right there. Okay, negative 2, okay, plus a 3/2. Ending out with a negative 1/2. And now I'm looking at the next one right here. Again, the y value, the negative 1 here, stays the same. Negative 1 being the x value. Now I'm going to add 3/2. Okay, so adding 3/2 to this gives me a positive 1/2. Okay, 3/2, the plus, I mean negative 1 plus 3/2. or 3/2 added to a -1 gives me a positive 1/2. Okay, and now this pair right here, the y value stays the same. Okay, the x value currently 0. We're going to add 3/2, which gives me 3/2 precisely. Okay, this value right here, 1, 1, this pair of value, this point right here at 1, 1, the y value stays the same after the parentheses. I mean after the comma. And then now 1 plus 3/2. Okay, 1 plus 3/2 now is a 5/2. Okay, it's a 5/2. And now the last one right here. So we have a 2, 0. The y value is 0. It stays the same. Okay, so now 2 plus 3/2. Okay, 2 plus 3/2. That gives me a 7/2 right there. Okay, 7/2. All right, so now with these points right here, these are the updated points, and I should have written them in blue ink, but you know, for one instance I forgot, and now consequently that's what we ended up with. But these are supposedly the points, the guiding points on the blue graph. And now we put these on the graphing space right there, okay, to draw our graph. All right, so now we are ready to put it in. All right, so now with our graph in full screen view right here. All right, so these are now the guiding points. Okay, these are now the guiding points. So they are just like those original guiding points on the parent function, but now they are all being shifted. See, so this point right here in blue is corresponding to that first point, and I can also put in the labels right here. All right, so now see minus 0.5, 0 for this point right here. It's corresponding to minus 2, 0 because it's 3/2 square grid. I mean it's 3/2 square grids away, or 1.5 square grids moved to the right hand side, and that point here is corresponding with this because it's 1.5 square grids moved to the right hand side. All right, and then you can pause the video to double check for consistency. And so now I'm expecting the shape exist just like this original shape right here between these updated guiding points. So I see a wave down, wave up, and hits down right here, and a straight line, and a straight line here. All right, so in that way, now it's time to draw the actual graph. Okay, so now I am going to draw through that. So as I said earlier, now we are expecting a straight line joining up, all right, to that first point, because that's what it is. Just like the parent function, it has a straight line, 40 degrees, 45 degrees line going straight up to that first point. It's just like that. That's how we get that blue one. Okay, and now after that break point, it's going to turn its way down as a sharp angle, but then goes as a wave here. Okay, so now I'm going to continue drawing that through these points. Okay, so imagine I'm trying to mimic that idea about if we were doing this with paper and pencil. All right, and so now I'm going to continue after this point right here, but I'm expecting a straight 45 degrees line coming up from there. So that's how it happens. All right, so now we got the graph. Okay, we got the graph of that shifted graph of that g of x function being f of x minus 3/3. All right, so now let's look at another example. And so now with the graph being currently shown, and let me still keep the graph here on the board. All right, so with that current graph right here, let's now look at another problem. All right, so now I'm going to write, how about in part B? Let's look at, for part B right here, let's look at how about g of x equals to, and I purposely write this in the common way that a lot of textbooks out there or have written it, but it's our responsibility to recognize that in the right way. How about g of x is defined as f, that parent rule right here, okay, but how about x plus 3, okay, x plus 3, f of x plus 3. Okay, so now here's my advice. This is a plus 3, So it's not quite telling us much. But now take that advice I've had earlier, take that teaching of mine I've had earlier. This doesn't show us, this is not clear for us about the shifting. So now write it this way. We want to see this as, so admittedly this is the original way how the problem is written, but now you do want to purposely write it as following. G of x is the same as f of x minus, all right, f of x minus, and then this is a plus 3, so now writing that as a subtraction operation, then we're subtracting negative 3. All right, we're purposely doing that because now once we have rewritten our expression here as a subtraction operation, then this is an indication that our problem will involve some horizontal shifting. I'm only saying it will involve some horizontal shifting. X minus, x subtract. And then that value right here now, depending on whatever that is, it could be positive, it could be negative, like in this case right here. That will lead us into, are we moving it to the right or to the left, by how far. All those information will be indicated through this value right here. All right, so now in that way, I recognize that A is a negative 3, okay, which is a negative value, clearly. That's how I see it, okay. And so now let's write down a couple expectations. I am expecting that, as far as an expectation, okay, it is expected that the graph, okay, is shifted. See, because x subtract. So now I'm expecting there's a horizontal shifting. So it's shifted, but now with that value being negative, okay, so shifted to the left. All right, so now that's the direction of the shifting, and then by how far? Okay, by absolute value. But you can just, for start, we can just say by 3. But 3 really came out from 3, or a precise way of saying just absolute value of minus 3. That's where it came from, okay? By 3, or absolute value of negative 3 units. And units here, I mean the square grids. We're moving by 3 square grids. That's how I'm interpreting it, okay? That's how we are interpreting it. But now, writing this, translating this thoughts process into the actual graphing work, and especially when we try to physically bring the graph and drag it to the right or drag it to the left, it's like I said again, it may come easy for somebody, but it usually comes as a challenge for a bigger group of people. So take this advice right here, okay? We're just simply going to add add negative 3 to every x values. So this problem is still drawing the same graph from the previous problem. It's the graph of f of x is still presented here, is still given here. So in that way, I'm just going to stay right on those, and you're still seeing that on the screen right there. I'm going to stay right on those guiding points, okay? And with those guiding points right there, I'm going to now pick just the x values and then add negative 3. Add a to every x values among these guiding points there. Again, theoretically, we can add a, we have to add a to every point on the trace of that graph. But here we can just focus on those guiding points, and then those guiding points will define the shape of our graph. Okay, let's get to it. Now I'm going to move to the other board. All right, so now I'm going to clear out this adjustment right here. All right, so the function we're doing here, the descendant function this time is f of x minus negative 3. That's how we're seeing it. And I've been spending a lot of time focusing on that explanation, on that interpretation right there. Okay, and now for my pairs of values among these guiding points right here, then this is how I see it. First pair, negative 2 comma 0. This is the y value. It stays the same. Okay, the x value was negative 2 on the parent function. Now negative 2 add negative 3. add a to every x value. -2, add -3 gives me a -5. Okay, so now we're going to start picking up pace right here. This next pair of values, the y value stays the same. The x value currently or on the parent function, -1. Now adding -3 is going to give me -4. Okay, and then similarly. So now on this next pair of values, 0 was the original, the y value on the parent function. It stays the same. Okay, just like that. So quite a few problems we've done so far. When it comes to a horizontal shift, okay, nothing is changed on the y values. Okay, the y value stays exactly the same. Okay, and now 0 add with -3. That gives me -3. Okay, and then on the next point, so now I can just throw these values in. Okay, so 1 stays the same because it's y value, and now it's this point right here is 1 plus -3, -2. Okay, and now 2 on the last pair of among the guiding points right here, 2 plus -3, that's -1. All right, so now we have an updated set of guiding points. Okay, I just now realized I mistakenly write these in black ink again, but gladly I still wrote these this sentence one in blue ink. So expectedly these are the guiding points on the blue graph right there. Okay, they stay with the blue column. So now on our graph in full screen view right here. Okay, on our graph in full screen view. I'm gonna allow me to bring that to the left hand side a little bit more. Okay, so all right, so now let's see what will happen to when as we draw the actual graph. So let's now put in the guiding points first. The guiding points are being printed in blue color right here. So these are now the guiding points. Okay, these are the set of guiding points right here. So they go from, see, that point here is the furthest point corresponding with this point. Okay, so let me now put on the coordinates, put in the labels of the coordinates right here. See, -5, 0 is corresponding with -1, 0. You see, and the reason I give out this advice simply because, see, you can see it through the graph already. Once too many points are being blended together, it's hard to recognize that. And that's why putting it through a chart like this, okay, putting it through a chart like this will keep things organized and be precisely clear. Okay, no matter if there's, you know, hundreds of points being involved there, but you can still have a way. All right, and so now with this particular, these are the guiding points. So that, once again, I was saying that one is corresponding to this. This here is corresponding to the bottom peak right here. Okay, even though commonly people call this a valley, but I see that as a peak away from the high, I mean from the x-axis, and then it comes back here. It comes back and hits. So there's a wave going through this, and then it should be a line joining up to that, and then another line drawn away from that. Okay, so my mouse cursor is already doing that action right there. But now let's really draw it. So I'm trying to make it look like we are doing that with paper and pencil. So here's how we're doing it. All right, so now let's look at the graph. All right, so now drawing the graph. With straight edge, we can make a straight 45-degree line connecting straight up to that. Okay, and then once we get to that point right here, then that's about the finishing point of the straight line right there, the straight 45-degree line. And now we're gonna start, and you see when we're actually doing this with paper and pencil, then it doesn't have to be, you know, perfectly on scale. You can be a little off, but that's not important. We're not competing with machines right here. All right, and so now we're getting that, okay, and then it's swinging up as a wave, swinging down. So make sure your graph, when you're actually doing a hand sketch version, it's going through all of these points right there, and then and now from that point on, it's gonna swing away as a line, a 45-degree line again, and drawing that away. So we use straight edge here, we use a straight edge here, and we just try our best to get that shape as a wave here. That's all it takes. Okay, that's all it takes to get the graph done. All right, so 2 problems done throughout this example 5 right here. Now let's look at an FYT right there for you to try on your own. All right. All right, so now on the same graph here as an FYT. fyt, let's call that, how about g of x here is defined as f of x plus 1. Okay, so this is one that you can try independently on your own right here. All right, so now go ahead and pause the video. The whole idea of an FYT is that I want to leave that for yourself to try independently. So I won't explain, I won't step in with any step anymore. I'm just going to wait until you are finished. And feel free to pause the video. And once you resume the video, I assume that you got an answer, you got your graph, and you got your guiding point successfully sketched together with that graphing screen right here. Okay, and so now go ahead and take your time. All right, so at this point, assuming you already had the table done, okay, and then successfully put it on the graph. So all I'm doing now is I'm gonna just quickly show the guiding points, okay, and the guiding points and with the graph. So again, this is the graph of the parents function. All right. So now these are the guiding points with label. All right, and you can double check with that. And now this is now the actual graph. All right, so now let's get into another class of problems where I call that example 6 right here. So let's look at example 6, and I'm still gonna retain this advice right here, okay? And we're still doing the horizontal shifts. So in example 6 right here, here's the worded instruction. Let's sketch the given function. All right, let's sketch the given function by recognizing it as a transformation of a known function. All right, as a recognizing, we want to sketch a function, the given function, okay, as a transformation of a known function. Okay, so let me highlight a few the key points here. So we want to sketch, meaning to sketch the graph, okay, and so that means we're doing that by hand. So now, by recognizing it as a transformation, we want to see the function, the given function here as a transformation. So sketching the graph, we've done this similar kind of problem often enough throughout this particular lecture here, but we don't want to go back and build everything from scratch. Say on whatever given function here is, we're going to build a table of values, and when x equals 1 and the output equals this, and when x equals 2, output equals that, and then we create the graph by tracing out the points. That's not how we're going to be doing the sketch right here. So the idea now is that we're going to look, before we make the sketch, we look at the function given here as a transformation related to some other known function. And that's why there are these terms right here, known function. So we want to see our given function here as a transformation of a known function. And then from that point on, we're going to take advantage of our understanding about the transformation. At this point, we're going to sketch the graph easily. Okay, so I had a little typo here, but sketch, I mean, of course, sketch the graph. Okay, sketch the graph of the given function by recognizing it as a transformation of a known function. All right, so here we go. Let's look at the first function. So first problem here that we want to sketch the graph. How about so g of x here? So g of x is already, any of the function we are graphing is, in a way how it is already a descendants function. Another way of saying the function given here is a descendants function, and we want to recognize which parent function this descendant came from. That's the idea. Whose child is this? Okay, So g of x, how about 1 over x minus 3. 1 over x minus 3. Okay, so there we go. This is the function that we want to sketch. This is the given function. Let me spend some time writing it. That can save me some more space later. So 1 over x minus 3. This is the function that we're aiming at. But now, before I'm throwing in the sketch, because we definitely, like I said, we definitely don't want to construct a table of values. That's taking way too much time. So, and right now I'm still explaining the thought process, so it seems a little bit long, but it will come a lot faster when you're actually doing that on your own, especially at the day when you're already fluent with your transformation skill right here. You see, this has a 1 over, and no special square or anything like that. It's just simply a 1 over. 1 over. So why not 1 over x? And so now all of a sudden we realize, hey, wait a minute, this is, I mean, think about this. We have seen this f of x equals 1 over x as a known function. Yes, this is a known one. The known one I can think of. It's like this. Because, I mean, doesn't have to be anything fancy, but it has a 1 over. So is there something in our mind, in our own memory, that has something with a 1 over? This one here. Because among the toolkit functions I've introduced earlier in some earlier video lessons, there are this reciprocal basic or simple reciprocal or reciprocal square. They all have that 1 over, but I chose this one simply because the descendants function we're looking at, he has no square or anything like that. So we stay with this simple reciprocal. Okay, so f of x is that 1 over x. So now with this known function, let's have a little closer look. So I'm showing as much details as I can about how I laid down my thought process, and then hopefully once you click with all that, then you can start having your own thought process, and when you're on your own track right there, it should be moving a lot faster than how I do it. Okay, but so in the way it seems like this f of x, I mean this g of x here, this seems like this g of x is 1 over. Okay, the way how I'm breaking down the given function right here, relative to this known function, then it seems like it's a 1 over something. 1 over some inputs. But then we put the inputs here, x minus 3 instead of the usual x. Okay, and now that's g of x. But now, so further I recognize, so this is, hey, wait a minute, this is really related with the parent's function by this function g of x is f of x minus 3. F of x minus 3. So now we recognize clearly this will cause the horizontal shifting transformation. And then the 3 here will decide how far we will shift it horizontally and where will it go horizontally, left or right. This value 3 right here. Okay, and so now, yes, the parent function has already been recognized here and being confirmed. Okay, and so now parent function, and we recognize that g of x being this in this form really is the parent function in the input x minus 3. All right, so now we laid down all the information we need. So that means a here is a value 3, that's positive. All right, so now I'm running a little short at space here. Let me rewrite that so that I can make some more space at the bottom line right there. But so this g of x being a 1 over the x minus 3. Okay, so now I'm going to throw in my expectation. As far as the expectation, I am expecting, okay, and when you actually, for anyone who is asked by your instructor to put in written work, this step where I'm showing my expected thought right here, my thought of expectation, you're not required, no one is required to write down your thought. You write down how you organize your thought, but what else you think, it's on your own. You don't have to show that. So here it's just because I have to present my thoughts to get you click into that routine right there. Okay? But so the expectation here is that we're gonna, the graph of f, of course, is shifted, okay, to there's a positive value, so it's shifted to the right. okay, by how far will that be? 3 units. Okay, and now since we have gone through example 5 earlier, so now I don't have to tear it too far down to absolute value of 3 or anything like that. We now just know it naturally enough. It's going to be 3. Okay, absolutely. All right, 3 units. 3 units. But then it's going to be so now we have enough expectation. Okay, but now in the end let's have a look, because once I mentioned about the parent function, what's in your mind? Okay, what's in your mind about the graph of this? Have a moment to have that. Take a moment before I pull up the actual graph of this parent function. Have a moment to have that, to retrieve that the graph of that toolkit function, of that particular toolkit function in your imagination, and then compare with what I pulled up here on the screen. Okay. And so now, hopefully you already had some imagination in your mind. Okay. This is the graph of the 1 over x function, the simple reciprocal function. Okay, it's a simple reciprocal function. Okay, so now with this simple reciprocal function, it has a few guiding points that quite famous. Just stay focused right on those points that falls on the grid right here. Okay, so now these are the guiding points. All right, and I can create a zoomed in version right here. Okay, so that means as an expectation, blending this imagination with our expectation, I'm expecting that so the term expected is hidden behind the graph screen there a little bit, but so for this g of x, I'm expecting that the graph of f right there is going to be shifted to the right hand side by 3 units. Okay, and so in that way, now let's get ready for that. So really, for g of x here being this, and we're shifting, see, like I've been saying that out loud throughout the whole example 5 and even before that, it's not that simple when we're actually sitting down on paper with paper and pencil and try to shift that as is. It's not that simple. It may come easy for somebody, but it's usually hard or challenging for a larger group of students and people. Okay, so stay with this advice right here. I'm going to add 3. Okay, add 3 to every x value. So now what this is the graph given currently, right? The x values, and so literally, I mean, or theoretically, we have to add 3 to every x value on that trace of the graph. But here we just need to focus right on the setup, the guiding points there, and add 3 on every x value there. Okay, so now in that way, let's move to the other board. All right. So now on this board, I am going to create a table. From what we have observed in this graph in red ink right here, which is still showing on the board, and I'm looking at a point being to the far left, it's a -2, comma, -1/2. So the y value there was a -1/2. The next point I see here is a -1, comma, -1, and the next guiding point here is going to be a positive. And actually, we can have another. The next guiding point here I see on my list is a -1/2, comma, -2. Okay, and then the next one down I have +1/2, comma, +2, and then I had 1, comma, 1, and the last one I had on my list there is a 2, comma, 1/2. These are all the guiding points, okay, on this particular function that we're on the graph of this particular function we're working with, the known function, that toolkit function. And so now this is, so in the version where the parent's function but being shifted away by 3 units to the right hand side, so on the version that's f of x minus 3, on that updated version. So for the first pair of value, okay, for the first pair of values, every y value stays the same, because the advice we've had here, and for this kind of transformation, for this elementary transformation, nothing is done with the y value. Everything is done for now on the x values. Okay, so negative 1/2 stay the same, just like that. So now minus 2, you're going to add positive 3 to minus 2. So now that's consequently results in 1. So minus 2 comma negative 1/2 now becomes or transform to 1 comma negative 1/2. Okay, so the next point now, y value stays the same again. Okay, this point right here, this x value, we are going to add 3 to that x value. So negative 1 plus 3 gives me a positive 2. Okay, and then this value right here, negative 1/2, and this point right here, negative 1/2 comma negative 2, y value negative 2 stays the same. Okay, and then negative 1/2 plus 3. Negative 1/2 plus 3 is going to be a positive 5/2. All right, positive 5/2. So you can always double check with your own understanding in adding and subtraction fraction. Okay, and then let's advance on. So this next point right here at 1/2 comma 2 right here, y value stays the same, being 2. Okay, but the x value here, 1/2 plus 3. Okay, 1/2 plus 3. All right, so that will give me 7/2. All right, and then for the next point, y value stays the same, 1. X value, we have to add 3 to that. So 1 plus 3, that makes 4. Okay, and then for the last pair right here, 2 comma 1/2. 1/2 stays the same because it's the y value. Okay, but the x value, we're going to need to add 3 to that. So here we're looking at 5 like that. Okay, 5 plus 2. All right, so that now has completed our list of the guiding points on the descendant function, the guiding points of the blue graph of the descendant function. Okay, and I actually reminded myself to use a blue ink this time for, in this example, for the g of x that we're drawing. All right, so now we are ready for putting all that into the actual graph right here. Okay, so now here's on my graphing space right here in full screen view right here. All right, so now I'm looking at, let me now show the guiding points. So the guiding points are these values. Okay, and let me also put labels. All right, so now let me put that in closer zoom so that we can realize the nature a little better. So that's from the left to the right, these guiding points go like this and like that. Okay, so that's from the left to the right. So now you can see a clear correspondence with these guiding points on the original parent function. It went like this and it went out like that. Okay, so that point here is clearly a correspondence to this, and this point here is corresponding to that point. Okay, and so on and so on. And so you can always pause the video and double check for the correspondence between these guiding points on the blue graph and the guiding points on the red graph right here. All right, and it's now time to draw the actual graph. Okay, so now just like that, through these first 3 guiding points on the parent function, the graph went like this. Okay, that's the shape. And so now through these, with these transformed guiding points right here, the graph have to go like this. Now, I will mention this a little later, but now once we draw the graph, okay. All right, see, the graph will come down just like that. All right, and then as I continue it, there's going to be another piece right here. All right, so that's the actual graph. Now, for this particular problem, for this particular graph right here, allow me to mention the following. The function, this reciprocal function here, when I was going over it, particularly in an earlier lesson, I was saying that this particular function has a phenomena that we call a vertical asymptote, okay, and a horizontal asymptote. So the vertical asymptote of this graph is, see, the idea about vertical asymptote, hopefully you don't have to keep having my reminder over here, but it's just a line, vertical asymptote or horizontal asymptote. Any asymptote is just a line where the graph will get close to but never cross through. Okay, so just like that in this picture, the graph in red gets close to the x-axis, okay, from the 2 sides here. So that vertical line, get close to the y-axis. So on this picture right here, the the red graph right here gets close to the y-axis, which is the vertical line right here, from both sides, but never cross through. So this y-axis was the horizontal, was the vertical asymptote, okay? And it's a vertical line. So now think of that right here. When we're in the transformed version, that horizontal asymptote gets transformed too. So with the parent function, when it's with the parent function, then the vertical asymptote is as x equals 0. This line right here, x equals 0. But now it's x equals 3 right here. Okay, it's x equals 3 when it's transformed. Okay, when it's transformed. So now let me quickly put it in. All right, and then I can change that to black ink with dotted line right there for you to make it real clear. All right, so that vertical asymptote, it was once here. It was here, and it's still here with the parent function. So if we're still looking at the parent function, then that vertical asymptote is here. But now for this blue graph right here, maybe let me change that to the appropriate color, blue as well, but dotted line. So now this graph in blue has that line x equals 3. So even the vertical asymptote gets shifted as well. It gets shifted horizontally to the right hand side and by 3 units. So every property that belongs to whatever parent function graph will be shifted accordingly, according to the rule right here. Okay, and so that's the idea about and that's the graphed version. Okay, that's how we sketch the graph, okay, of this given function. All right, so now let's move out to part D right here. All right, so in part B of our graph, okay, in part B of our graph, let's look at, so how about g of x is given to be, okay, so how about 1 over x plus 1, okay, x plus 1 all square. 1 over x plus 1 all square. 1 over x plus 1 all square. Again, in our responsibility as a requirement in this problem, we don't want to use the table of values to build the graph of this thing from scratch. And the worst thing I should have mentioned also in the earlier problem, I should have mentioned the worst thing is to just completely rely on the technology. I use Desmos a lot, but that doesn't mean I let Desmos draw this thing for me from A to Z. Okay, I use Desmos to demonstrate the idea of how I understand about the graph if I would sketch that by hand. That's the idea. Okay, so the worst scenario here would be you just simply throw, hey, here you go, give that to the calculator and get it graphed. That's not the idea. Okay, we want to see if we can possibly sketch this by recognizing a known function. Okay, and from that known function, we're going to think of this function g here as a transformation. Okay, so here's my thought process again, and you're already in gear with this kind of problem, so it can start picking up a little bit, the pace a little bit. It's a 1 over, but there's 1 over, similar to the reciprocal function we've done earlier. Okay, but now it's a 1 over square. 1 over a square. Okay. So if I search back in my memory, I remember we've had something like this. How about 1 over the square of the input? F of x equals the square of the input. And yes, this is one among our toolkit functions. Again, one function among our toolkit functions. The rule says on this particular one right here. So now clearly this is known. Okay, clearly this one here is known function. That's the one. Okay, and now the way I see this rule says on every input x, we're going to take the reciprocal of the square of that input. The reciprocal of the square of the input. Okay, so now in the way how I see that, so it looks like I recognize, so g of x here being the 1 over the square. Being the 1 over some square. That's how I'm seeing it. And then seems like in this square here, I just put in that x plus 1 inside of that. So I mean, observe my order, how I put details in. 1 over, first thing is an empty square, and then we put that x plus 1 in there. You can always roll back the video to see my action with a certain order, with a certain sequence of action right there. And that means we realize that this is really related with this parent function as what? F of x plus 1. F of x plus 1. Okay, so clearly I see g of x is related to the parent function. But this relationship here with this plus sign is dangerous in a way how I have been explaining. We want to see x subtract a value so that it clearly indicates for us, even though this is admittedly the way how very commonly many textbooks out there are writing it. Okay, but now we want to see this as f of x minus, okay, minus negative 1. Okay, x minus negative 1. Now that tells the story very clear, crystal clear, because now this x minus or x subtract operation tells us that we have a horizontal shifting. It rings a bell about the horizontal shifting. And then now our a value here, our a here is a negative 1 value. Okay, so now make note of that. So a here equals negative 1, being negative. All right, so now after all that, let's throw in some expectation. So as an expectation, okay, with what we're expecting, and see, I don't even need to, I'm not even worrying about the graph right now yet. Okay, so what expected here is that the graph, okay, the graph is shifted. The graph is shifted. All right, where is it? Where are we shifting it? The graph is shifted to the left-hand side. Okay, after taking that little note right here, the graph is lifted to the left. Okay, I apologize for such a narrow board space right there. Shifted to the left by how far? By, okay, 1 unit. 1 unit, or you can think of the 1 as absolute value. Okay, absolute value of negative 1. That's where ultimately it came from. Okay, so by 1 units, and units I mean the square grids on our graph right here. That's what it is. Okay, that's an expectation. So now let's look at the graph. Let's look at the graph. All right, so this is the graph of our reciprocal squared function. Okay, so this is the reciprocal square function, 1 over x squared right here. That it's one among the toolkit functions. Okay, and I already put in the guiding points right here. So we have a few guiding points. So this is negative 2 comma 0.25, which is of 1/4 right here, positive 1/4. So the whole graph stays above the x-axis. So all y values are positive. Okay, needless to say. And you can always you can always pause the video to have a clear understanding how these points are consistent with the rule of the function. Okay, being the rule of the function being a 1 over x squared. And now let me keep that graph together with the screen here. Okay, so the rule of the function is 1 over x squared. That's why we're seeing that. And then those are the guiding points being recognized already. But now we want to take that graph, and this time the expectation is here. We are expecting that the graph is shifted to the left. So that same graph, we're going to bring that to the left by how far? 1 square unit. Okay, 1 square unit. So that means every guiding point there is going to be brought to the left-hand side by 1 unit far. Okay, but see, so now, and this is particularly where doing this advice is going to help right here. The shape is getting more complicated. Okay, and so without relying on these guiding points and without relying on this, it's going to become a lot more challenging to just think about, to just imagine about taking the graph. Because believe me, any textbook shows you this expectation. They say it out, okay, shift the graph to the left, shift the graph to the right by how far. But then when they actually showing it, they still going to have to put behind the scenes and right in front of what you're seeing, those guiding points. But didn't make it specifically clear that you need to focus on those. That's the one part I found in a lot of textbooks, that they still using the guiding points, but they never mentioned it specifically, that there are those guiding points right there that guide your graph, that helps your work easier. That's why I have to spend my time in making it a little lengthy about these graphs, where I keep focusing on those guiding points. Okay, so now I'm going to add a or negative 1 to every x value in the guiding points. Technically, we have to add that to every x values on that graph you're seeing. Okay, but here we only need to add a negative 1 to every x value among the guiding points. Okay, so now let's head to it. I'm going to go over to the other board. And now clear out my table here. All right, so the function, the transform, the descendant function this time is f of x minus -1. So again, I always want my students, whoever learned with me, to see an x minus operation here as an operation that rings a bell about we have a horizontal shift. Okay, and now these are the guiding points. So on the original graph, we're looking at -2, 1/4. Now, admittedly, Desmos, see, every technology has a limitation. Desmos does not show fractions on the graph. We have to live with that. Okay, but it's better that we work with different situations so that we understand, we have a broader understanding. So 0.25 on Desmos. Desmos shows -2, 0.25 in fraction is a 1/4. Okay, and then we're looking at -1, okay, 1. Okay, these y values are all positive, and then we're looking at -1/2, okay, but 4. All right, and then we're looking at +1/2, 4. We're looking at +1, 1, and we're looking at 2, 1/4. That's how it is. Okay, so these are the guiding points. We have 6 guiding points on this particular parent function. Okay, the reciprocal squared. Okay, so now once we display this nature of our descendants function, it came out from the parent function. Shift the graph to the left by 1 unit. Okay, so now I'm going to add -1 to every x value. So again, all of these y values stay the same. And now at this point, we've done that tons of times, so I'm going to start picking up the pace here on the y values. So here, y value is 1/4. Okay, needless to explain. That's -2. I'm going to add -1. That makes -3. Next point. Now 1 stays the same because it's y value. -1, I'm going to add another -1. That gives me -2 because these are the y value. These are the y values. We're supposed to add -1 to every y value. So the guiding points make no exceptions. That -1/2, 4. So now 4 stays the same. -1/2 plus -1. That gives me. Be careful with your fraction. So if you're feeling a little shaky with your fraction, review your fraction skills. This is -3/2. Okay. Now next one, 1/2. Okay. 4, 1/2, 4. 4 stays the same. 1/2 plus -1. That gives me a -1/2. Okay. And then the next one here, 1, 1. So 1 for the y value stays the same. 1 plus -1. That gives me a 0. So 0, 1 is the updated points. And then here we're looking at 1/4 here for the y value. Okay, 1/4 for the y value. And then here we're looking at +1 because 2 plus -1 is a +1. Okay, so these are the guiding points for the updated graph, for the g of x. Okay, and so we're going to rely on these to draw the curve. And the shape of the curve, the shape of the graph will look just like the shape of that parent function in red ink right there. Okay, so now on the graph. All right, so now on the graph, this is the parent function. Okay, so I apologize that I forgot to put this in the corner of when I was still on the other board, but here it is again. This is the parent function. So now I'm going to show the guiding points for so now I'm going to show the guiding point for the descendants function in blue. So these are the guiding points. All right. So with labels here. So let's double check for consistency right here. And you can always, let me put that in a smaller view together with the other board so that anyone can double check for consistency. And I can zoom it in even a little more so that these points can become a little more spaced out like that. Okay, so that point here is corresponding to this point and being 1 unit shifted to the left. That point is corresponding to that, same height but being shifted to the left. That point just like that, see, when now it becomes somewhere in the middle between grids, they're making it harder when you're actually drawing that without these guiding points. That's why having these guiding points will help tremendously. Okay, all right, so those points, those guiding points are consistent with what we're having here on our chart. Like that. Okay, so use a chart technique is one favorite technique of mine that I've been using throughout all my time doing this. And again, I'm passing this down to whoever learning it with me. Okay, and so now, back on the graph. So now once we've had all the guiding points successfully nailed down right there, and after you have already confirmed, so now let's draw the graph. Okay, so here's the graph of my, and think about if we sketch the original parents function, it went like this. Look at the motion of my mouse cursor. That's how it's tracing out the actual graph. Okay, so now when I see these guiding points right here, then I'm going to be tracing it just like that through these guiding points in blue. Okay, and so now here's how it works in precise scale like that. All right, so there you go, and then again just like that, and I can slow down the pace a little bit. Okay, but now all of a sudden we realize the graph in blue here looks exactly like the shape of the graph in red. Okay, but being a shifted version, being shifted away. That's all there is. Okay, so let me hide away the graph of the original parent function. So now it's that graph of the descendants function is still here. And so I also need to mention, just like how it was in the earlier problem, this 1 over x squared here, the parent function originally had a vertical asymptote as well. Okay, on the picture, let me hide away the descendants function. The original parent function had a vertical asymptote at the y-axis, or x equals 0. And so now think about we have already shifted that descendant function. I mean, we shifted that parent function to the left by 1 unit right there. Okay, so that we created so that this would become the graph of the descendants function, and these are the guiding points. So now think about that. Where would that vertical asymptote be? Because this is in the end is still it's still taking all that property, all of those properties from the parent function. So I am expecting to also see a vertical asymptote. So that vertical asymptote here, it was at 0 as x equals 0 for the parent function. Now shifted to x equals -1. Okay, x equals -1. All right, and that's how I see the vertical asymptote right here. All right, that's what it is in dotted line right there. Okay, compared to the original parents. Okay, the original parents has the vertical asymptote right on the y-axis, x equals 0. All right. And so now, before we're leaving this example, I will put in another FYT problem. Okay, I will put in an FYT problem for anyone to try. And again, so it's an FYT. That means I am expecting that you are going through your own process right there. Okay, think of the process I've been doing here, and hopefully you have already caught some highlights among those processes right there. Okay, and so to get your own do your own problem, I will only show the final answer. Okay, the final graph right there. All right. All right, so here's our FYT. Okay, so for this FYT, okay, let's sketch, and I want to leave that for you to work on that independently for anyone who's studying with me. So g of x equals, how about square roots, okay, of x plus 2. Square root of x plus 2. So notice the x plus 2 is completely inside the square root. All right, so now go ahead and feel free to pause the video to spend your own time, spend as much time as you want. Okay, mess it up 100 times and keep fixing it. You will learn better. The more mistakes you make, the better it gets. Okay, but now I'm going to let you pause the video. Okay, and now assuming that you came back from pausing the video to get your own problem done, then I would see that without showing you the thought process, the known function, that known function, okay, should be or dependent function, square root of x. Okay, that's the starting, the important starting point right there. And now I am going to show the graph. All right, so this is the graph of the original parents function that I have already pointed out. Okay, and so now and I already had these guiding points placed here, and you should have had your guiding points here as well, and you should have had a way to know that these are the guiding points. So now this is our function. The actual g of x is here. All right, so what I see now is that it's the same as that parent function being shifted to the left-hand side by 2 units far. And let's now put in the guiding points on blue right here to make it real clear about how these points are all being shifted. Okay, so that point is correspondingly being shifted to here. That point is being shifted to here correspondingly, and so on and so on.